The James Webb Space Telescope, JWST, has made one of the most extraordinary breakthroughs in our understanding of the universe, challenging long-held beliefs about the early cosmos. For decades, scientists have believed that the universe, shortly after the Big Bang, went through a period called the Dark Ages. During this epoch, which spanned roughly 1 billion years, it was thought that the universe was a place devoid of light. This was largely because the universe was filled with dense clouds of neutral hydrogen gas, which blocked the passage of light. The traditional view has been that during the Dark Ages, no stars, galaxies, or any other light-emitting objects existed, rendering the universe essentially dark and cold. This belief has held for decades, but the groundbreaking discoveries made by the JWST are now turning this theory upside down. The telescope's advanced infrared capabilities have allowed it to peer deeper into space and further back in time than any telescope before it. What JWST has uncovered has shaken the scientific community to its core, as it reveals that light did indeed penetrate the so-called Dark Ages, opening new avenues of research and challenging the basic tenets of our understanding of cosmic history. At the heart of this revelation are the Lyman alpha emissions, a form of radiation that is generated when ultraviolet light from young, hot stars interacts with surrounding hydrogen gas. These emissions are particularly significant because, although the universe was once shrouded in dense hydrogen clouds, they appear to have managed to escape from the early galaxies, reaching us even through the cosmic darkness that was once thought to have enveloped the universe. Scientists have speculated that this was made possible by the formation of bubbles or channels of ionized hydrogen around the first stars and galaxies. These bubbles, created by the intense radiation emitted from these first stars, would have ionized the surrounding hydrogen, making it possible for the Lyman alpha emissions to pass through the previously opaque hydrogen clouds and travel across space. The fact that these emissions are visible to us today suggests that there was much more light in the Dark Ages than previously thought. The JWST's ability to detect Lyman alpha emissions with unparalleled clarity has provided new insight into this period of cosmic history. While earlier telescopes, like the Hubble Space Telescope, had detected faint signals from the Dark Ages, it was only with the launch of the JWST in 2022 that scientists have been able to confirm that Lyman alpha emissions from galaxies existed in far greater numbers and strength than anyone had imagined. This new information paints a very different picture of the early universe, one where light was more abundant, and stars and galaxies formed far earlier than expected. The strength of the emissions detected by JWST suggests that the formation of the first galaxies and stars was far more widespread and intense than we previously realized. The discovery that galaxies from the Dark Ages were not only forming earlier but also were surprisingly bright and large challenges the older models of galaxy formation. Previous theories had suggested that galaxies and stars would take a much longer time to form in the early universe. Yet, the findings from the JWST suggest that the process of galaxy formation was much faster and more efficient than once believed. The early galaxies that the JWST has observed are already advanced, shining with intense star formation and remarkable luminosity, and they provide clues to how the first galaxies took shape in the infancy of the universe. As we examine these galaxies, it becomes clear that the first stars were not only capable of ionizing their surroundings but also significantly impacting the intergalactic medium. The rapid formation of stars in these galaxies hints at the potential for a far more complex and active early universe. These discoveries also challenge the very notion of the Dark Ages, which had been assumed to be a time when no stars or galaxies existed and the universe was entirely opaque to light. The finding that galaxies were already forming and emitting light at such an early stage suggests that the universe may have been far more dynamic and illuminated much earlier than we once thought. This new view of the universe is reshaping our understanding of the timeline of cosmic evolution. It raises the possibility that the process of reionization, the transition from a dark, opaque universe to one where light could travel freely, may not have occurred in the way that scientists once envisioned. The traditional model of reionization proposed that after the Big Bang, the universe was dark, and over time, as the first stars and galaxies formed, they began to ionize the surrounding hydrogen gas, allowing light to travel freely. However, with the discovery of Lyman alpha emissions from early galaxies, it appears that the universe was already becoming transparent to light much sooner than previously thought, suggesting that reionization may not have been a gradual or slow process, but rather something that happened more quickly than anticipated. Furthermore, the JWST has uncovered several galaxies that existed much earlier than expected, with some dating back to just 400 million years after the Big Bang. This discovery is especially important because it was once thought that such galaxies would have been impossible to form so soon after the universe's inception. The fact that these galaxies exist and show such advanced properties, like high star formation rates and large sizes, presents a serious challenge to our previous models of galaxy formation. If these galaxies were able to form so early, it suggests that the processes behind galaxy formation may have been much more efficient than we thought, and that the universe may have developed in ways we have yet to fully understand. Among these galaxies, one of the most notable is GNZ11, a galaxy originally identified by the Hubble Space Telescope. When it was first discovered, there was skepticism in the scientific community about its age, with some speculating that it might have been a measurement error or an outlier. However, after the launch of the JWST and the subsequent confirmation of its existence, scientists now know that GNZ11 truly does date back to just 400 million years after the Big Bang. The JWST's spectrometers have revealed strong Lyman alpha emissions from this galaxy, further confirming its advanced stage of star formation. The existence of such an ancient and well-developed galaxy so early in the universe's history has profound implications for our understanding of how galaxies form and evolve. Another significant discovery is the galaxy MAX 0647 JD, which is part of a very early galaxy cluster. This galaxy is faint and was thought to be a small, relatively insignificant object in the early universe. However, JWST's observations show that MAX 0647 JD exhibits strong Lyman alpha emissions, indicating that it is undergoing a massive burst of star formation. The fact that a galaxy of this size and age is able to produce such intense star formation raises further questions about how galaxies evolved in the early universe and how the conditions of the cosmos allowed for such rapid growth. Additionally, the JWST has identified a galaxy known as EGS-8P7, which lies about 13.2 billion light-years away. This galaxy is particularly noteworthy because it exhibits strong Lyman alpha emissions that suggest it was able to create bubbles of ionized hydrogen around itself. These bubbles would have allowed the Lyman alpha emissions to escape, revealing a surprising level of activity in such an early stage of the universe. The discovery of this galaxy reinforces the idea that the early universe was far more dynamic and luminous than we had previously believed. Perhaps one of the most mind-boggling discoveries made by the JWST is the detection of a supermassive black hole at the center of GNZ11. This discovery is groundbreaking because it challenges our understanding of how supermassive black holes form. Traditional theories suggest that these black holes form from the collapse of massive stars or from the merging of smaller black holes, processes that take billions of years. However, the supermassive black hole at the center of GNZ11 exists just 400 million years after the Big Bang, a time when such processes should not yet have been able to occur. This raises the possibility that black holes could form in different ways, potentially through the rapid accretion of gas in the early universe or through the influence of exotic forms of matter and energy that we don't yet fully understand. The existence of such a massive black hole at such an early stage in the universe's history suggests that the dynamics of galaxy and black hole formation were far more complex than we previously thought. It forces scientists to reconsider how black holes grow and how they might have played a role in the formation of galaxies in the early universe. The presence of these early black holes challenges conventional wisdom and opens up new lines of inquiry into the nature of the universe's earliest epochs. As scientists continue to study the data provided by the JWST, they are faced with a profound dilemma: are our traditional models of cosmology and galaxy formation correct, or have we been fundamentally misunderstanding the history of the universe? The discoveries made by the JWST suggest that the universe may be far older and more evolved than we once thought. In fact, the very idea of the Big Bang, as well as the traditional timeline of the universe's development, is being called into question. While many scientists are still trying to reconcile these new discoveries with existing theories, others are exploring alternative ideas that might better explain the rapid formation of galaxies, stars, and black holes in the early universe. The work of the JWST is far from finished, and with each new discovery, the scientific community is presented with more questions than answers. The discoveries made so far suggest that the universe's early history was far more complex and luminous than we previously realized. The detection of Lyman alpha emissions, the discovery of galaxies that formed much earlier than expected, and the detection of supermassive black holes in the early universe all point to a universe that was far more active and illuminated than we once imagined. As scientists continue to analyze the data from the JWST, we may be on the verge of a new understanding of the cosmos, one that could fundamentally alter our view of the universe's origins and its evolution. The data from JWST is opening up entirely new fields of study in cosmology and astronomy. In the future, scientists will likely continue to refine our models of galaxy formation and black hole growth. They will use these new insights to better understand the processes that shape the universe we see today. It's possible that the discoveries made by JWST will eventually lead to a complete overhaul of the standard cosmological model, potentially changing our view of the Big Bang, the Dark Ages, and the formation of galaxies. However, the scientific community will need time to digest these findings and integrate them into our current understanding of the universe. In the meantime, the James Webb Space Telescope continues to make groundbreaking discoveries, pushing the boundaries of what we know about the cosmos and expanding our understanding of the early universe. The mysteries of the Dark Ages, once thought to be beyond our reach, are now being revealed before our eyes. The universe is no longer a dark, opaque place. Instead, it is a bright, dynamic environment where galaxies, stars, and even black holes were forming much earlier than we ever expected. The discoveries made by the JWST are opening up a new chapter in the history of cosmology and astronomy, and we are only just beginning to scratch the surface of what we can learn about the origins and evolution of the universe. The future of space exploration has never been more exciting, and the possibilities are endless.